conservation of mass, and the control volume. A control volume is a volume in a space of interest for a particular study or analysis. The surface of this control volume is referred to as a control surface, as we said also before. Of this control volume. Is referred as control surface, and always consists of a closed surface. The size and shape of control volume are completely arbitrary and so are defined as the best suited to analysis to make it. The surface may be fixed or may be moved so that it expands or contracts. The surface may be fixed or it may move so that it expands or contracts. However, the surface must be defined relative to some coordinate system. In some analyses, it may be desirable to consider a rotating or moving coordinate system and to describe the position of the control surface relative to such a coordinate system. The surface must be defined relative to a coordinate system. And to describe the position of the control surface, relatives such as coordinate, mass as well as heat and work can cross the control system. Mass as well as heat and work can cross the control surface. And the mass in the control volume as well as properties of this mass can change with time. The mass in the control surface as well as its properties can change with time. The next picture shows a schematic diagram of a control volume. Shows a schematic diagram of a control volume that includes heat transfer at this point, steam radiator, shaft work, turbine, steam turbine work, moving boundary work, expanding piston, for example, accumulating of mass within the control volume, and several mass flow. There is a mass flow, for example, here, and a mass flow here, and also a mass flow to the turbines. It is important to identify and label each flow of mass and energy and the part of the control volume that can store mass accumulation. Let's consider the control of mass. The control consider the conservation of mass, and then control conservation. Law as it relates to control volume, the physical law concerning mass. Recalling from section 5.9, say that we cannot create or destroy mass. We will express this law in a mathematical statement about the mass in the control volume. To do this, we must consider all the mass flow into and of the control volume and the net increase of mass within the control volume. A somewhat impaired control volume we consider a tank with a cylinder and a piston and two parts attached as shown in the picture here. This picture shows a control volume with the mass flow and some work and heat transfer maybe. Anyway, the rate of change of the mass inside the control volume as shown in this relation, dm control volume, the rate of change, can be different from zero if we add or take a flow of mass out as equals to, let me write from a previous rate of change plus in minus out. So we can write d and control volume on dt if the tank has a input and output flow. M dot E. This is a conservation of mass. You can also obtain this relation with the Reynolds transport theorem, fluid mechanics. The fluid mechanics course also available in the channel, which states that if mass inside to the control volume change with time, it is because we add some mass or take some mass out. There are no other means by which the mass inside the control volume could change. This equation expressing the conservation of mass is commonly termed the continuity equation. So, conservation of mass or continuity equation. While this form of equation is sufficient for the majority of applications in thermodynamics, it is frequently rewritten in terms of the local fluid properties in the study of fluid mechanics and heat transfer. In this book, we are mainly concerned with the overall mass balance and thus consider this equation as the general expression for the continuity equation. The more general, the more complete continuity equation can be obtained from Reynolds transport theorem formulation. Since this equation is rewritten for the total mass, ampered form inside the control volume, we may have to consider several contributions to the mass. So if we have total mass Such a summation is needed when the control volume has several accumulation units with different states of the mass. Let us now consider the mass flow rate across the control volume surface in a little more detail. For simplicity, we assume the flow in a flowing part. Consider the pipe. We assume the fluid is flowing in a pipe or duct illustrated. Flow fluid flowing in a pipe or duct as illustrated here. We wish to relate the total flow rate that appears. The equation of mass to the local properties of the fluid state. The flow across the control volume surface can be indicated with an average velocity shown to the left of the valve, or with a distributed velocity over the cross-section as shown to the right of the valve. The volume flow is rate volume which is equals to the dA V is positive. And the mass flow rate which can also replace to this relation. We can obtain the mass flow rate, the volume, m dot mass flow rate, integration of V local dA dA on, where often the average velocity is used. It should be noted that this result has been developed for a stationary control surface, and we tacitly assume the flow was normal to the surface. This expression for the mass flow rate applies to any of the valid flow stream entering or leaving the control volume, subject to the assumption mentioned. The next section is the first law of thermodynamics for a control volume.